Very good morning and welcome to the lecture series session on EC 402 Nanoelectronics. I am Professor Ravindran giving the classes here. My dear students, in the last class we have discussed about the formation of silicon oxide. What are the different techniques or process through which we can produce silicon oxide? We have seen thermal oxidation method in which dry oxidation, wet oxidation, that is dry oxidation process and wet oxidation process. Then we have seen the CVD process, a type of CVD process that is what's called the POI, tetraethyl orthosilicate. That process through which we can produce or we can deposit silicon oxide on wafers. Then we have seen the anodic oxidation and its disadvantages. Then we have seen that the silicon oxide, that is through ion implantation. How ion implantation techniques can be used for the deposition of silicon oxide on silicon wafers. So today we are going to see how can we fabricate nanoparticles or how nanoparticles could be produced. What is a nanoparticle? A nanoparticle is defined as a ball or a ball-like molecule which consists of a few tens to some 10,000 atoms interconnected by interatomic forces. That is the definition of a nanoparticle. A nanoparticle is defined as a ball or ball-like molecule which consists of few 10 to 10,000 atoms interconnected by interatomic forces. That is a nanoparticle. The deposited nanoparticle layers are different from uniform layers, particularly due to the presence of grain, that is rough boundary. Usually, the nanoparticles are also fabricated upon the wafers or surfaces of material in the form of uniform layers. But the difference is that when nanoparticles are actually formed, which may have presence of grains or rough boundaries. So this actually makes the difference from the deposition of different types of films like silicon oxide or so in nanomaterials. Okay. So now we have to know how nanoparticles could be fabricated. What are the different fabrication techniques or what are the different methods used for the fabrication of nanoparticles? The main methods followed for the preparation of nanoparticles are grinding these ion bonds. A very simple technique, I will explain to you that. Then laser ablation method. Laser ablation method we have already seen. We have discussed about the molecular beam epitaxy. In that particular epitaxial method of formation of films, we have seen how laser ablation method is used. In the same way, for the production of nanoparticles, laser ablation method could be used. Then reduction methods. What is meant by reduction method? Reduction method means that is the reduction of, that is chemical action between materials, metals and some kind of oxides or so, or different kinds of materials or different kinds of chemical materials in the form of liquid or solid form, and which under the action of some temperature environment or so, these materials could be reacted to each other, then and reduced to, and that the process of reduction takes place. Actually, the reaction is actually a process of reduction that gives the outcome as nanoparticles. That is the reduction method. We will see that reduction method, how this reduction method could be used for the production of nanoparticles. Then self-assembly. Self-assembly means the assembly of these material particles together by some chemical actions. That is a self-generation, or that is why it's called self-assembly of the material over the surface of the wafer or the material surface. Then the sol gel process. Sol gel process, I have already told you, that can be used for the preparation of silicon oxide. We will see how silicon oxide could be used with the method of sol gels. What are the important techniques involved in that? That will be discussed here very in a detailed way, of course. And sol gel process, the process of sol and gel formation, and the different processes involved in that one, that will be discussed in the production of nanoparticles and all those things. Then the precipitation of quantum dots. How quantum dots could be fabricated? Of course, quantum dots are actually fabricated just like the fabrication of nanoparticles. These dots are actually particle size formations on the surface of the material. So these are all the important things which comes under this fabrication of nanoparticles. Now we will discuss about one by one. Okay, grinding with iron balls. What is meant by grinding with iron balls? This basically the name itself gives some kind of indication of what this particular process is. In this method, a container is filled with stainless steel balls of few millimeters in diameter. Small steel balls of size of few millimeters diameter is actually contained in a container of this particular device setup. The material to be crushed is added. That is, material to be crushed means the material of which the nanoparticles are to be formed. That is, the material to be crushed is added in the form of a powder of about 550 micrometer diameter grain. Actually, the material whose nanoparticle is to be produced is of the size of about 550 micrometer diameter in grain size, and that is actually crushed in this particular device chamber. Okay, in that chamber, this small steel balls are contained. Okay, after filling the container with liquid nitrogen, actually this process is taking place under the presence of nitrogen, liquid nitrogen. Okay, so this container is consisting of this container is always having a inlet of this particular liquid nitrogen. Under this particular gas, presence of this particular liquid nitrogen, this particular process of producing nanoparticles are done. Actually, there is a rotating shaft in that particular device, in this particular uh, ball mill, and that rotating shaft will be going on rotating. And when it is rotated, these balls and all the materials will be crushed. Ball will be crushed with the material whose nanoparticles are to be produced, isn't it? So the grinding is usually done with the help of the rotating shaft provided in that ball mill. Actually, this arrangement as a whole is called grinding ball mill, and here this particular process is called grinding with iron balls. The grinding periods are within the range of minutes to some hours, say 100 hours or so, like that. So here this grinding period depends upon the type of size of the nanoparticles to be produced. So since it's a nanoparticle, size is very well defined. So in order to get that nanoparticles, the grinding, that is the rotating shaft, will be rotating throughout for some hours, some minutes to some hours. And how this particular, or what is the advantage of using this particular type of ball mill? This ball mill actually causes to produce, for this ball mill with its operation under the liquid nitrogen environment and the rotation of the shaft causes to make the crushing of this materials with the steel balls due to the rotation of the shaft. So that actually crushes this particular material and forms the nanoparticles of nanocells. And as far as the advantage of this particular method is concerned, this is a very simple method. So process is very simple. But what is the disadvantage? The disadvantage is that the grinding balls may sometimes contribute impurities to the nanoparticles. grinding balls. This balls which actually is actually moving along with the shaft when it is rotated. So then what happens? This ball will be, that is a steel ball, that will be crushing the material, isn't it? So that actually causes to contribute. Sometimes it may contribute some impurities to the ball. So that the nanoparticles produced may not be that much pure sometimes. Of course, this particular method is very commonly used in the preparation of nanoparticles, even if this particular small disadvantage is there. Okay, now we will see the grinding ball and the arrangements. So this is the ball mill chamber or container. In which these are all the steel balls. So this is actually the milled powder. Actually, the milled powder means actually the powder of which the nanoparticles are to be made of size 50 micrometer is actually put here, and the milling balls is actually the steel balls, and then that it will be having some millimeters of size actually. And here this is the inlet point of the nitrogen gas. This inlet, that's the liquid nitrogen gas. Under this particular environment, this particular process taken place, and this is actually airtight compartment of this particular container, and this is the gas outlet. And this is the spindle or the rotating shaft which rotates so that all these materials along with the balls will be revolved due to the revolvement of this one, so that the balls will be crushing the materials here. So that crushing actually causes to produce materials of nanosurface. Okay, so this is the ball mill arrangement for the fabrication of nanoparticles. So this is quite simple to understand. Now we will see gas condensation method, how gas condensation method can be used for the production of nanoparticles. In this particular method, the operation occurs in an evacuated chamber with a pressure of 10 raised to minus 5 Pascal. This operation, that is the gas condensation method, the operation, that is preparation of this nanoparticles are occurring in an evacuated chamber with a pressure of 10 raised to minus 5 Pascal. That means that evacuated chamber will be having a small gas which is filled at a pressure of very small pressure, that is 10 raised to minus 5 Pascal, of the order of 10 raised to minus 5 Pascal. After mounting the raw material on one or more crucibles, it is evaporated thermally by an electron gun or by ion sputtering. Usually, you can use the raw material of which the nanoparticles are to be produced, that can be kept on one or more crucibles, and that can be either evaporated by evaporation techniques, or you can make use of electron gun for evaporating it, or you can make use of ion sputtering. All these methods we have already seen. Of course, this is the arrangement of this particular process, and this is the chamber in which these are all the crucibles, that is evaporation source which is produced here, and this is actually heated up on the crucible. The material whose nanoparticles are to be produced, and that is heated up, that is placed here. That one or more number of crucibles may be here available here. Okay, this is the main chamber. And this is the separator, and liquid nitrogen will be allowed to pass through this one, through this regimen. Of course, in most of the phenomena taking place for the production of nanoparticles, liquid nitrogen, this particular process are taking place under the presence of liquid nitrogen. Okay, so this is the inlet point of the liquid nitrogen, and here this is the funnel, and these are all the arrangements, bellow anvil arrangement for these are all fixed position, and there are vacuum pump in order to make the pressure here to with an inert gas of almost 10 raised to minus 5 Pascal or so, and then slider for sliding this one, what low pressure compact units, and all those high pressure compact units, see all those things system. Of course, this is actually a system for inert gas condensation of nanocrystalline powder. I told you, even if it is evacuated chamber, that evacuated chamber will be filled with a small, or with inert gas with a very small pressure of the order of 10 raised to minus 5 Pascal. Under that particular condition, along with the liquid nitrogen presence, this particular phenomena of nanoparticle formation takes. Okay, with this idea, we will discuss this gas condensation method. Okay, so after mounting the raw material on one or more crucibles, it is evaporated thermally by an electron gun or by ion sputtering. So that what happens, this particular material will be this particular material will be getting evaporated fumes or if it's plumes in the form of vapor, that is material vapor will be available here. Okay, that's it is shown like this. Now what happens? The evaporated atom or molecules united and form particles of different sizes. So evaporated atom which comes more as a vapor form or molecule, and that molecules unite and form and form particle sizes, isn't it? The molecules which comes above that particular crucible in the form of vapor, that will be actually unite together as molecules and which forms particles of different sizes. Finally, they are captured and collected with a funnel, and that is here shown here. And finally, when it is condensated, that is why it is called gas condensation method. When the liquid nitrogen, when it is under the presence of liquid nitrogen, this gas condensation will take place. Actually, this particular vapor is condensated and the particle of nano size will be then condensated and that will be made available to collect here through a funnel. This is the funnel. On that funnel it is collected. Okay. Now, uh, the particle diameter is usually within the range of 5 to 15 nanometer. So the particle size which condensated here is actually in the size of 5 to 15 nanometer, well within the range of a nanometer part or nanometer, that is well within the range of a nanomaterial or particles, nanomaterial particle or nanoparticle. Okay, so that is a nanoparticle. Okay, now that is what is called this condensation method. So I think you understood the condensation method now. So it's a simple method. This is the arrangement. This arrangement, of course, this arrangement mainly is requiring, or this arrangement has mainly a chamber in which this reaction takes place. What is the reaction? There will be crucibles, one or more crucibles, in which the material whose nanoparticles are to be produced, or that is to be produced, isn't it? So then these two crucibles will be kept up in a particular temperature. So that will be usually done with the help of evaporation technique or by the help of electron gun method or by the help of ion plating. This method, our ion plating, ion sputtering method. So that sputtering method actually causes to make this material will be in the form of a vapor, and that will particles in the form of molecules and its atoms will be come over this one as a vapor, and that will be condensated on the presence of liquid nitrogen here, so that condensed particles will be now available on the funnel which is placed here. So with this particular arrangement you can just draw the particular condensation container, that is gas condensation container, and the methods and all those things, and you just know the basic procedure of this one. And in order to evacuate this particular chamber under which this particular process are taking place, and vacuum pump is there, and vacuum pumps create a small pressure of inert gas here, so maybe an argon gas or so, and that will cause to make the pressure under which this particular process are taking place of the order of some 5 millipascal of 5 pascal, right? 5 pascal, not 5 10 raised, but how much pascal? What is the pressure involved in that one? 10 raised to minus 5 pascal, not 5 pascal. 10 raised to minus 5 pascal, very small pressure. 10 raised to minus 5 pascal. Okay. Now, these are all the arrangements to take this collected or condensated or collected nanoparticles here, that will be taken through this one, and so that this is a slide and through which it will be taken, and there are some arrangements made for the sleeve and all those things. High pressure compact unit, low pressure compact unit, all these are there, and there is an anvil here, then bellows are here. So these are all the that arrangements for collecting this nanoparticles. Okay, so this is the gas condensation. Essentially, this method involves vapor formation of the materials whose particles are to be produced, and that is condensated with a liquid nitrogen gas, and that is collected then through a funnel and taken for the and that is collected for nanoparticle or for the formation of nanoparticle. Okay, so that is the idea. Then the next method is the laser ablation method. What is laser ablation method? Laser ablation method we have already discussed in the case of formation of nanofilms, nanolayer films or nanolayers or nanofilms. So the same procedure is taken place here also. These are all the arrangement. Of course, I need not repeat again and again because these are all the substrates formed, and substrate actually is having no. These are all this is the substrate, and these are all the target in which the material whose nanoparticles are to be produced, and that is to be then treated with the help of lasers through some laser beam like excimer or Yagi. Laser beams are the uh, uh, right excimer, either excimer laser beam or that other kinds of CO2 laser beams are. So different kinds of we have already seen different kinds of uh, laser beams possible for the production of lasers for keeping the surface of the target, right? So excimer is one among the laser beams which we may be used here, and this is the length provided for this concentration of this laser beam upon the target. Here, this target will be usually revolved with the help of a revolving motor and all those things. And this is actually a read equipment. That read equipment can give the layers formed here, the nanoparticle layers formed here, that can be very clearly shown, and that can be very easily characterized with the help of this characterization device and all those things. Okay. For the formation of this one, of course, or toxin and all those things that make this particular chamber uh, very low under a very low pressure. So this particular pumping arrangements and all these things are available. So anyway, you have to draw, you have to learn this particular drawing very clearly, and you should know each and every part of this one very clearly. What is the function of the read equipment and all those things, and there will be lead also. Apart from read, there will be lead also. Lead also, you know what is in the lead, right? You refer your notebook and see what is lead and what is auger, Raman spectroscopy and all these equipments and that. And this is actually a heater used for heating the surface of substrate. And because all this particle formation, all those things are done under the presence of, under the heating of the substrate surface. Okay. Now we will see the process. The removal of a material from solid surface by this technique of laser ablation is known as laser plume ablation, that is LPA. So I told you plume of the material is available by the target by concentrating the laser beam upon the target. So the removal of material from solid surfaces means solid target surfaces by the techniques of laser ablation is known as laser plume ablation. So figure shows this arrangement. This arrangement I have told you, I have explained all these necessary parts upon this laser ablation method. Okay, now we will discuss. The raw material is provided as a solid. Raw material is provided as a solid. Its dissolution is achieved by a focused laser beam. Actually, the target material whose nanoparticles are to be deposited is directed towards a laser beam. Actually, a laser beam is there, the external laser beam we have seen here, and this particular material is dissolved due to the focusing of the laser beam upon the target material. Okay, deposition takes place in an ultra high vacuum or in the presence of some neutral gas such as argon at a certain pressure. That already we have discussed about the argon gas. Its importance for the process taking place instead of a laser ablation setup, right? The gas at the desired pressure is used to control the deposition rate as well as film deposition. The gas at the desired pressure is used to control the deposition. Actually, this gas, why this particular process taking place under the presence of some inert gas like argon? Because this particular gas at the desired pressure is used to control the deposition rate. So how much deposition has to be made upon the wafer surface, and that can be controlled with the help of this gas at, with this particular desired pressure. Okay, a hyper pulse laser is usually pulse lasers are used for the laser ablation technique. That is what we have seen in the formation of nanofilms also. Pulse lasers are used. Okay. When the laser fluence, that is laser power density, that exceeds the ablation threshold value for the material, the chemical bonds are broken and the material is fractured into energetic fragments, typically a mixture of neutral atoms, molecules and ions. അതായത് ഈ ലേസർ ബീം ടാർഗറ്റിലേക്ക് ഫോക്കസ് ചെയ്ത് കഴിഞ്ഞാൽ when the temperature is such that the laser beam will produce temperature upon the surface of the ടാർഗറ്റ് മെറ്റീരിയലിൻ്റെ നാനോ പാർട്ടിക്കിൾസാണ് നമ്മൾ ഉണ്ടാക്കുന്നത്. അതുകൊണ്ടാണ് ടാർഗറ്റിലേക്ക് നമ്മൾ ഈ ലേസർ ബീമിനെ ഡയറക്റ്റ് ചെയ്യുന്നത്. So when the laser beam focuses upon this target material, due to the fluence, laser fluence, laser power density, and when it exceeds the ablation threshold value of the മെറ്റീരിയലിൻ്റെ ആ പുറമേ നിന്ന് അതിനെ വേപ്പറൈസ് ചെയ്ത് പോകുന്നതിനുള്ള ആ കെമിക്കൽ ആ ടെമ്പറേച്ചർ വാല്യൂ അതിന് ദാറ്റ് ഇസ് ദ ത്രെഷോൾഡ് വാല്യൂ അതിനേക്കാൾ കൂടുമ്പോൾ when the laser fluence power density, fluence means power density, the laser power density exceeds the ablation threshold value for the material. The chemical bonds are broken. So what happens? The surface of the material, the chemical bonds are broken and the material is fractured into neutral atoms, molecules and ions. So when the temperature is going on increased due to the focusing of the laser, what happens? The surface of the material, the material will be fractured. That will be actually fractured. The surface is getting fractured into energetic fragments of what? Of neutral atoms. Sometimes it may be neutral atoms or molecules and ions. It may have neutral atoms possible, molecules possible and ions possible. That will be in the form of vapor, in the form of plumes. We say the plume. Since these fragments are highly energetic, this process is considered as an explosive operation. Usually, these fragments of the surface of the target material is under high energy. So, what happens? This process is considered usually as an explosive evaporation, and usually this evaporation method can be considered to be an explosive one because the surface is getting fractured due to the focusing of the laser. Okay. Most of the absorbed energy is deposited in the ejected material. So most of the absorbed energy is deposited in the ejected material so that there is little or no thermal damage to the surrounding target. So usually, when lasers are targeted upon the surface of the target, there may have certain damage occurring on the surface. But here you should see that the energy absorbed, that is completely deposited upon the ejected material, that is completely transferred and that is available on the ejected material, so that this ejected material will be usually converted as that will be usually condensated as the nanoparticles over the substrate. Okay, so that is why at the target material there is no thermal damage occurring due to this application of laser. So the thermal damage is not occurred because whatever is the absorbed energy that is deposited in the ejected material. So ejected material means the material that is to be converted as, or that is to be used as a nanoparticle, that material particle that is converted as a nanoparticle, that is the ejected material. Okay. The vapor, sometimes the vapor is called a plume. The vapor is collected on the substrate, placed a short distance from the target. Actually, this vapor is placed very near to the target level. So that's why this plume can be very easy. This vapor can be very easily deposited upon the target surface. Okay. The advantage of this procedure is that a 1:1 transfer of the material composition from the raw material and to the particle. So that is the main advantage. The main advantage is 1:1 transfer of the material composition from the raw material to the particle. Usually, whatever is the raw material available, whose nanoparticle has to be produced, then whatever energy in the form of laser beam we apply on the target level, whatever is the amount of energy absorbed by the system, that is absorbed by the target material, and that is transferred in the form of energy in the ejected material, that will be available in the form of plume, in the form of vapor, or we say that plume of the vapor or plume of the material. So here a 1:1 transfer of the raw material to the particle is taken place. That is the main advantage of this one. Okay. So that is the laser ablation method. So you should understand basically the laser ablation equipment. So this equipment and necessary parts and this target material, these are all the raw materials or target materials of which the nanoparticles are to be deposited over the substrate material. So substrate material is just above this one, above this one means very near. It is actually some millimeter to centimeter away from the target material, and this target material can be rotated with some automatic rotation arrangement so that a uniform, why this is rotated uniform, uh, uh, that condensation of the material or uniform condensation of the plume of the raw material is done upon the soil. There will be uniform deposition of the material of the target. Okay, so that nanoparticles deposited here will be uniform in nature due to this. Okay, so this is laser ablation method. Now we will see the reduction method. How reduction methods can be used for the production of nanoparticles. So this methods you should understand very clearly, and whenever a main question is asked, what are the important techniques involved in the production of nanoparticles, or what are the different processes of production of, what are the important methods of producing nanoparticles. Then you have to mention all these processes, that is grinding with iron ball, gas condensation, then laser ablation method, then reduction method, then the sol-gel process and like methods. Okay. So now what is this reduction process? Reduction process, I told you, it is essentially a chemical reaction through which the material the particles are formed. When chemical reactions are taking place, the chemical reaction causes to produce the particles of the material which is to be produced as nanoparticles. So this method employs the chemical reduction technique. So it's actually a chemical reduction technique. The reaction is actually a reduction of the material. This reduction techniques for deposition of nanoparticles. So in reduction method, the chemical reaction essentially causes to reduce, or it is a chemical reduction which actually make use of producing, or which is actually made use of producing nanoparticles. That is the reduction method. So some examples I have given here. Some metal compounds like chlorides, some metal chlorides. Okay, some metal chlorides can be reduced to elementary metallic nanopowder by the application of NaBeT3H. What is NaBeT3H? That is sodium. Na means sodium borotriethylene hydride. Similarly, this LiBeT3H, lithium borotriethyl hydride. So these are all some kind of chloride formed materials. So here this is sodium, this Na means sodium borohydride, sodium borohydride. So this particular powders can be used, or that can be used, or that it's an example. By using this kind of materials, or this kind of high, sodium borotriethyl hydride, lithium borotriethyl hydride, or sodium borohydride, which can be used for uh, activating or for reducing chemically the material which can be deposited or which can be used for the production of nanoparticles. So this is actually so nanoparticle can be made, or nanoparticle can be produced by the application of these materials, chemical materials, that is sodium borotriethyl hydride, lithium borotriethyl hydride, sodium borohydride, and these are all the reaction takes place where is actually the chemical reduction technique that actually causes to produce what? Produce the nanoparticles of the material. And the material, of course, these are all actually the chemical reaction reagents actually, and this reaction agents is actually causes to reduce due to the that is what is called chemical reduction. So the chemical reaction is actually a chemical reduction, and that chemical reaction gives out what gives out the nanopowder. So that's the importance of this material used for the chemical reaction. Okay. Now, example, metal and ethyl. M is actually standing for metal, Et is standing for ethyl. The reaction can be written as MCl, metal chloride. X actually X can be 3, 2 like that. That is 2 NaBeT3H. BeT3H means we have seen here sodium boroethyl trihydrate. Sodium borate triethyl hydride. And this is actually a reagent which actually causes to make this reaction with this chloride in order to form the metal nanoparticle, metal plus XNaCl, sodium chloride, and actually XBE3 plus 2XH3. This X actually stands for whether it is 2, if it is chloride, then it is 2 chloride, 3 like that. Okay. So that's why it is mentioned here X. Actually, if this is 2 means MCl2 means here M NaCl, the 2 NaCl like that. So BET3, 2 BET3 like that. 2 X, actually 2X means 2 into sometimes it is 2 into 2H. So 4H2, that gas, that is 2 into 2 means 4H2 as a gas. That actually makes here in the form of molecules here. So this metal, that is actually metal produced as nanoparticles, which will be deposited over the material. Okay, so this is a simple example for this one. And M stands for metal, whether it is a sodium, whether it is any other kind of chloride, so many zinc chloride, say metal zinc, sometimes copper chloride, like that. So it's a metal, and ethyl means Et. Et represents ethyl. Okay, for this reaction. And this reaction essentially here is a reduction, actually it's a chemical reduction. And this chemical reduction actually causes to produce the material as nanoparticles. So that is the importance of this method. When the same metal chlorides are reduced in tetrahydrofuran solution, metal carbides are obtained. Okay, so this is also when the same metal chlorides are reduced in tetrahydrofuran solution, when the same chlorides are reduced, so when the same chlorides are reduced in the tetrahydrofuran solution of the same metal, so actually then what happens? The metal carbides are obtained. So metal carbides, that particular metal carbides are obtained in the reaction as an outcome. Okay, so that's an example actually I have quoted. So you just understand what is the reduction technique. So how reduction technique is used for the production of nanoparticles. Essentially, this method is a chemical reduction method. The chemical reaction means it's a chemical reduction method with the use of reagents like sodium borate triethyl hydrate, lithium borate triethyl hydrate, and sodium borohydrate. So that are all chemical reagents which actually cause us to make chemical reduction possible here. And that chemical reduction actually causes us to produce the nanoparticles of the material. That is, if that material is a metal, then that is a metal particle. Okay. So that is all about this reduction method. So with this we complete the session here, conclude the session here. In the next class we will discuss about the remaining, that is the self-assembly methods, and then the precipitation of quantum dots and the methods employed for that one. Okay. So I think you have just understood the concept and all. Just go through the notes. I have given the notes very clearly. You just go through the notes, and I have given the notes page by page so that you can view the notes very clearly. You just go through it, and if you have any doubt, we will discuss it in the Google Meet class. Of course, tomorrow you will be having a Google Meet session for doubt clearing and other things, whatever things you feel with regard to this class and that you can just respond to me. Okay. Thank you very much for patiently hearing my session. Thank you very much.